record on the computer. Okay, so I guess we're recording and sharing and everything. And okay, the only thing that remains is to, okay, so it will be a course about physical kinetics. It's a rare occasion where there's a field in physics which is very important, but there's actually not so many good books about it. Actually, there are only advanced books on physical kinetics, and none of them is devoted to solid state physics. So, of course, you can use the Lifshitz-Pitaevsky textbook on physical kinetics, but I must warn you that this book is probably too broad, and I don't know any good book which is focused on this subject. So that's why I decided to give this lecture series. So what is physical kinetics is about? And I will be teaching physical kinetics from the perspective of solid state theorist. So I'm interested in transport and electronic transport in materials. I'm interested in things like charge transport, energy transport, all types of responses that are measured in the real metals, semiconductors, and such structures. So I'll try to present a theory, a framework, how we understand transport in these materials on the most intuitive level. So I think physical kinetics allows us to study transport, to study non-equilibrium phenomena in the most intuitive physical manner, and to build some understanding, qualitative understanding of the phenomena. So this is essentially the biggest advantage of physical kinetics as opposed to other ways of thinking about transport, that it allows to look at the problems, allows to look at the phenomena in very informal and very physical, intuitive way, and to build some physical picture of the problem. And I'll be focusing only on the normal state of matters, which means I will be not talking about superconductivity. I'll be only interested in the state of transport in normal metals. And I'll show you how you can describe transport in these systems, how you can account of various types of interaction in the problems. So this will be essentially the body of this course. Okay, so I assume you know nothing about physical kinetics. And I'll start with describing the fundamental equation, the only equation that essentially physical kinetics uses. It's called the Boltzmann equation. So Boltzmann equation, Boltzmann equation, it was invented by genius physicist Boltzmann, and it was fundamentally very difficult for people to understand from the very beginning, and many great scientists rejected this approach for various reasons, and it took people a while to understand the meaning of this equation and to learn how to use it. And later on, much later, that Boltzmann equation was invented. People learned how to derive this equation systematically, and people invented mathematical machinery that now allows for rigorous derivation of this equation under different conditions. But this happens like a century after the Boltzmann equation was conjectured. So now let me describe to you Boltzmann equation. I'll be using some simple example, and I'll be talking about Boltzmann equation for electron gas. So what is electron gas? Well, let us think about non-interacting electrons. So there is a body, a big box, and this big box is full of particles. And these particles form a many-body system, and we want to understand this many-body system in general out of equilibrium. So how we approach this problem? And okay, so you have all learned statistical physics, and you all know that if this is a system of fermions, then if the system is left alone and allowed to equilibrate, it will eventually wind up having a state of thermal equilibrium, which means that electrons will be distributed among different energy states, and their distribution will be given by Fermi Fermi distribution function. So what it means? It means that if you draw the distribution function.
What is the notation under F?
Okay, so F here stays for Fermi.
Okay.
And epsilon here stays for energy. And mu here stands for chemical potential. And T here stays for temperature. So this is something that we learned from statistical physics, that if you put lots of fermions in a box, and you try to you describe the system in the framework of statistical physics, you consider the statistical ensemble, then there is a single particle distribution, which is the probability to find a particle for a given energy, and the probability to find a particle for a given energy at equilibrium is given by Fermi statistics, and this is the function that that I just wrote. And it knows about two parameters, two external parameters. One is a temperature, and another is a chemical potential. So you have two independent ways to control the system, one by temperature and others by chemical potential. Now, this is a very simple and basic formula, though there are many thinking that went into this formula. So there are several things that are implicitly implied here, and let me set them out loudly. So when we write this formula, we assume that there is a system of non-interacting particles which has a finite temperature and has a finite chemical potential. So what does it mean that it has a finite temperature, and what does it mean that it has a finite chemical potential? It means that the system is A, at thermal equilibrium, and B, it reached the state of thermal equilibrium that allows to exchange two things: number of particles and energy. So you have a box inside of which there are lots of fermions, but we assume that the temperature inside this box is fixed and not the energy. So what it means that actually that this system is embedded inside some bigger system that we can call bus, a thermal bus, that allows to exchange energy between the degree of phase system, the subsystem we are interested in, and some bigger bus that exchanges energy between this system and the thermal bus. In addition, this distribution, and as I wrote it, assume that we control chemical potential and not the number of particles. It means that there is a weak link assumed that allows for particles inside the system to go out. So there is a particle exchange between the system and the bus that allows to reach the equilibrium. So essentially from the practical point of view, our sample, the system with electrons, has some weak link connection to the outside world that allows to establish energy relaxation and the particle relaxation. So you can think about this as an experiment where the system is placed inside the bus and there is some energy relaxation and particle relaxation channel that are open. So these are the things that being assumed implicitly when this formula is written. And what this formula suggests that regardless of what is the way of this particle exchange and energy exchange, in the long-term limit, there is universal energy distribution, there is universal distribution of particles with respect to their energy that has this absolutely universal form. It's called Fermi Dirac distribution function. And it also this function, it also very knowledgeable function. It knows that the distribution function, so at zero temperature, if I draw this function at zero energy, at zero temperature, this function takes two values, 1 and 0. So all the state with energy below chemical potential are occupied with probability 1, and all states above chemical potential are empty with probability 0. So these 1 and 0 are manifestation of Fermi statistics. you can put only one fermion into quantum mechanical state. So this equation knows not only about thermal equilibrium, it also knows about quantum mechanics. It also knows that statistics of these particles is of Fermi-Dirac type, and all fermions, regardless of whether they are electrons or other, I don't know, atoms with Fermi statistics, any particle with an odd spin will have, any system of particles, if you let it relax for sufficiently long time, will have this distribution function. So this is universal knowledge that quantifies the state of thermal equilibrium. So this function belongs to the realm of statistical physics of equilibrium situation. And this is not the subject of physical kinetics. Physical kinetics addresses, roughly speaking, the following question: what happens to this distribution function if system is pushed away from thermal equilibrium? So how we quantify the distribution of fermions, to be specific? I'll be mostly or maybe only interested in fermions, how fermions are distributed in their phase space if the system is driven out of thermal equilibrium. Okay, so this is our question, and we will now develop an intuitive way how we solve this question. Okay, so let us look at to be concrete, let me now look at the method. So what is the method for me? Okay, so let me remind you that metal is first of all a crystal. So it's a periodic array of atoms with some underlying crystal symmetry. It's a crystal with an underlying crystal symmetry and a certain state of occupation. So what do I mean by that? So we take a non-interacting electron model and we put it in the periodic potential. We put it in the periodic potential and we get that the Schrödinger equation has an eigenstate that can be parameterized by some energy bands. So E and K is an energy of electron with with quasi-momentum K in the band N. And what it means that there is a continuous index K and there is energy En of K and there are multiple.
Would you please go up a little bit so I could copy?
Up is here.
Yeah, yes, thank you. Thank you.
Can we continue?
Yes, thank you.
Okay. So there are solutions that look like this, and this is called the spectrum of electrons. And these solutions are called bands. Now, this is the general situation for any periodic potential. So once we have a periodic potential, we'll always have a solution that looks like this with emerging bands, and the function and the wave function of electrons will always have the following form. It will be parameterized by the index of the band and the quasi-momentum, and always be exponent I, K, R times U, N, K of R. K is being a vector, R being as a vector, and N being an integer number. And this is called Bloch Theorem. And it also says that function Un sub k r is a periodic function where A is a crystal vector. So if you perform a shift which transforms a crystal to itself, this shift is described by vector A. It's a vector of crystal what are they called, transformations, and then the wave function is always given by this expression, and there is a corresponding energy E n as a function of k. What people frequently do, is in many cases, is to approximate this function by at the bottom of this band or any other band, to approximate it by parabolic approximation, or like this, and in this case to replace the function E of k by k squared over 2m star, and this is called effective mass approximation. This is what people usually do in courses like solid state bond physics. But the main point from our perspective, that there is a thing that is called the spectrum, and this spectrum is associated with the periodicity of the underlying crystal. Now, there is another ingredient of this story. It's a chemical potential that decides what part of the states are occupied and what parts of the states are not occupied. So, for example, if the chemical potential lies here, that all states below chemical potential in this band are occupied, and all states above this chemical potential are empty at temperature equal to 0. And it's also clear from this picture that all higher bands are empty. This situation corresponds to a metal. And what it means that this system has gapless excitations that are available at low temperatures. If, however, for the same spectrum, the chemical potential lies here, that's a new position of chemical potential, the same system, the same spectrum, then the entire band beneath it is occupied. So it means that this situation, the band number 1, this band, is occupied, the band number 2 is empty, and there is a final gap between these two bands. In this case, there are no gapless excitation in the zero temperature limit. And in this case, this system is an insulator. So when chemical potential is equal to mu2, this spectrum corresponds to a spectrum of an insulator. And when the chemical potential lies in the position 1, this system is a metal. So this is roughly the distinction between metals and insulators. Now let me look at the situation which we describe as a metal and try to think about transport in this system. Let us first focus on the simple situation when there is only one band. So I'll drop the index of the band, so I'll have epsilon of k will be an energy as a function of quasi-momentum in the conductance band. Conductance band for me is the band which is not fully occupied. This is the conductance band. This will be the band that is responsible for transport in such system. So let me focus. So I'll drop the band index, and I will not be using words quasi-momentum. I'll just calling it momentum, but essentially it's quasi-momentum. So now let me think about electrons in this band, and let me think about low temperature limit. So what is the low temperature limit? It means the temperature is much smaller than epsilon Fermi. So my distribution function, it has Fermi jump as a function of energy. As we saw from the Fermi-Dirac distribution function, this jump is smeared on the scale of temperature. So within this window, distribution is different from 0 or 1. And I assume that the temperature is much, much smaller than epsilon Fermi. So if I think about phase space, if I think about states, I can picture thermal equilibrium where nothing depends on the coordinates in the lateral coordinate. And so my phase space consists of lateral coordinate and the momentum. So semi-classically, I divide my phase space into cubes. And I can ask what is the occupation of the phase space, and then in the simplest way, all states with the momentum smaller than Fermi momentum will be occupied with the occupation number 1, and all states outside of this sphere will be empty. And Fermi momentum is defined as P, as energy of P Fermi is equal to epsilon Fermi. And in the simplest case of parabolic spectrum, when energy of P is equal to P squared over 2m, this means that epsilon of P Fermi is equal to P Fermi square over 2m is equal to epsilon Fermi. So I have a sphere of the radius P Fermi. All states inside this sphere are occupied. All states outside this sphere are empty if temperature is equal to 0. If the temperature is finite, then there is a strip here of the order of thermal momentum where states are neither fully occupied nor empty. This is the vision of this is my vision on the non-interacting metal from semi-classical perspective. I'm looking at this quantum mechanical problem in a semi-classical way, and this is how I visualize the states of electrons inside the metal at equilibrium. So this is what you all learned in the courses like solid state 1, statistical mechanics 1, and so on. Okay, now we want to take this thing and try to generalize it outside of the thermal equilibrium. And we want to continue thinking about this system in a semi-classical way. So to do this, I still want to use my distribution function description. I want to think about single particle distribution function and describe how many fermions at the state with the momentum P, coordinate R at the time T. So what do I mean by that? Once again, I'm thinking about phase space of many body system, and I'm using a description based on two non-commuting operators. A momentum operator and coordinate operator. Now, from the basics of quantum mechanics, we know that if you have a coordinate and if you have a momentum, there is an uncertainty relation that requires that this to be larger than. So these two quantities simultaneously do not commute and cannot be measured. So strictly speaking, within quantum mechanics, I cannot define a position and the momentum of the particle at the same time. On the other hand, I know that in the classical physics, I can describe my particles using both momentum and the coordinate. So let me try and cheat a little bit and use this description in physical kinetics, and then we'll discuss what got lost and what did we capture.
How did you define the function f?
Okay, so function f is a generalization of Fermi distribution function outside of equilibrium. So I'm essentially using the same definition that was used at thermal equilibrium. So what do? I'm going back to my phase space. And I'm saying, let me imagine that my particles are put inside the big box. So there is a big box there. This box is called metal or sample. This sample has a boundaries. Boundaries imply that momentum or quasi-momentum of particles is quantized. Now, let me hypothetically divide my sample into cells. So this will be a cell of a phase space. So phase space is so if we're in the d-dimensional space, phase space is 2D dimensional. So it has one coordinate, which is momentum, another coordinate, which is a coordinate, is a real coordinate. So if you have one-dimensional sample, you will have momentum kx and coordinate x. If you have three-dimensional sample, you will have kx, ky, kz, x, y, and z. 6 coordinates that show a position of a particle in this phase space. It's a purely classical object from classical mechanics. You have a classical particle, you can describe its motion in the phase space. And the phase space has 2D dimension. Then you say, let me divide the phase space into cells of an unknown size. So I'm choosing something which I call delta K and delta R. And this is delta R is the size of the cell. The size of the cell in the real space, and delta K would be the size of the cell in the momentum space. And I now have a cell. So if I try to draw it in 3 dimension, I will have cell. There is one component delta X, another component is delta Kx. And if it's 3-dimensional, so it's a 6-dimensional cube. So this is one-dimensional version of what's going on in 3-dimensional system, one-dimensional version. I've chosen delta X and I've chosen delta Kx. These are the volume of my phase space, the volume of this cell is right now delta Kx, delta X. Now there are some particles that are in this cell. What do I mean by particle in this cell? There's a number of particles in this cell. I will call particles that are in the cell if they have a coordinate. They have a particle has a coordinate x, and it lies in this interval. So if this point will be x0, this point will be x0 plus delta x. So if particle has a coordinate ranging between x0 and x0 plus delta x, I would say its x coordinate lies in this cell. I can also talk about the momentum of the particle. So if this coordinate is k0, and this is k0 plus delta k, then all particles that have a momentum in this interval, they lie in this cell. And now, this is the standard picture of statistical physics if I'm looking at statistical physics at the many-body statistical states from the semi-classical perspective. And now what do I want to say? How can I look at this thing and when it's meaningful? So first of all, I know that electron has a wavelength. It has a natural size, natural length. And to look at electrons as a particle, to look at the electron as a particle with a given coordinate, I must have a resolution which is way below lambda Fermi. So for me, electron has a natural smearing, and this is lambda Fermi. So to determine whether it's in the cell or outside of the cell, my cell has to be much larger than lambda Fermi. Otherwise, there is no meaning to say the particle is in the box or the particle is outside of the box, because at the scales comparable with lambda Fermi, there is no in or out, there is no particle. It's a wave of the size lambda Fermi. So my delta K must be much larger than lambda Fermi. And similarly, I want to be delta K sufficiently large, and we will discuss what sufficiently large means. But I want the cell to be sufficiently large, then the number of electrons inside, will be equal to the volume of this cell, delta K in the power d, d being a dimension, delta X in the power d. It's a special dimension, times the density of electrons in the phase space. So this is number of electrons in the cell. This is the density of electrons in the phase space. And this density of electrons in the phase space is precisely the function f I was talking about the whole time. So if system is at thermal equilibrium, this function f, k, and r has a universal shape of Fermi-Dirac function that depends on the momentum via its energy. But what if the system is outside of thermal equilibrium? So this is exactly the question that physical kinetics answers. So the goal of physical kinetic is to compute the density of electrons in the phase space. Did I answer your question? And do you have any more questions? Hello?
It's okay.
Okay. Okay, fine. So, so now let us think how we approach this question, and let us think about the case where system is driven out of equilibrium by applying external fields. So let us assume that system was at equilibrium, and then there was an external electromagnetic fields that act on this system. Now, how the density of electrons in the phase space evolve? So now we are interested in the evolution of density in a phase space with time. Well, any idea?
Can you repeat the question, please?
So what is the evolution? What is the evolution of the density in the phase space in time, of this time? We have electrons, they were at equilibrium, they reached Fermi Dirac distribution, and then we applied, and then there are some electromagnetic fields that were applied on this system. How we can describe the evolution of particles in the phase space?
Do you hear me?
Yes, I do.
So can we assume that we still have this Fermi Dirac distribution, but the energy now depends on time? As we know, how like how electrons interact with electromagnetic field. So we can write a contribution to the energy and just substitute it to the Fermi-Dirac distribution, something like that.
That would be a very reasonable assumption, provided there is a well-defined Fermi distribution. Now let us recall what it required us to have thermal distribution. So thermal distribution emerged as a result of equilibrium. Now, here probably is something that I should have discussed but didn't. How come that Fermi distribution emerged as a result of equilibrium? Why did it emerge, and how do we know it emerged? And this is something that is probably not appreciated enough in the courses of statistical physics. So when you open your statistical physics textbook, there is a model of non-interacting electrons. Then there is a reminder. There's a model of non-interacting electrons. There is a Hamiltonian of non-interacting electrons. H, whatever that means. Then they would tell you that there is a density matrix rho, which is exponent of minus h k over temperature. And this is the Hamiltonian. And this is the density matrix. And you can build from here a single particle. From here, you can build a single particle. In case the problem is non-interacting, that this matrix is diagonal. And the elements diagonal matrix. And the elements on the diagonal are precisely equal to single particle distribution function. Now, but the thing is that was a little bit misleading. And the reason why it's misleading is precisely reflected in the equation that you just asked. So imagine that you act on electrons with some external electric field. So what the external electric field will do, if you have a Fermi surface and there's electric field that acts on this surface, so it will start to accelerate electrons. So it will essentially create electron hole pairs. There'll be an electron, there'll be a hole. You act for longer, you will take more electrons from within the Fermi surface, and you will create more holes inside Fermi surface. So the state will be less and less resembling the equilibrium Fermi distribution. Now, nevertheless, if electrons interact, and this is something that we'll be discussing and then towards the second part of our course, then there'll be equilibration of particles and holes, and then there'll be a redefinition or redistribution of the Fermi surface, And then, indeed, you're right, we will end up in the situation, where the time-dependent and position-dependent Fermi surface. But this happens provided that time of interaction, let me write, very vaguely write it, type of interaction between the electrons is short. In other words, we'll be looking at the system at time scales longer than some electron-electron interaction time. And then system will relax into some quasi-equilibrium state, and then in this case, you'll be absolutely right. Let me now look at the absolutely opposite limit. Let me assume that there is no interaction between electrons. No interaction between electrons. So electron-electron interaction time is infinity. And ask how system develops, how system evolves in this case. What will describe the evolution? How can I describe the evolution of the density in the phase space in case there is no interaction? Sorry, C is not a vector yet. How it changes in time. Now, and let me give you a hint. So F is a probability. F is a probability to find a particle in a certain state. Now, being a probability means that F is a conserved quantity. If there is a more probability to find a particle in a certain state, it must be a lesser probability to find in another state. Now, if you want to use hydrodynamic analogy, F is a density of particles in the phase space. Now, and if you know how density evolves, say from hydrodynamics, you know that density satisfies a conservation equation. Because density is conserved, any quantity which is conserved satisfies a conservation equation. So, which means that its full derivative with time is equal to 0. So I'm thinking about electrons as a fluid that flows continuously in the phase space. So I have a distribution in the phase space that allows to flow continuously. Now, this fluid is made of many particles. Each of them is moving in accordance with classical equations of motion. So if I have an electron, what it means that if there is an electron and it has a position r, has a coordinate r, and the momentum p, I know how these coordinates change in time from the classical equation of motion. I know that the time derivative of r is equal to velocity of this particle. If I know that the time derivative of the momentum is equal to electric field plus Lorentz force.
Can you please go back a little bit? Why did you say the evolution is 0?
I'm saying that the full derivative of the density of distribution inside the phase space is 0, because if you want, if I have a fluid, just a reminder, if you have usual hydrodynamics, and I have density of particles say density of particles, then I'm saying d density of particles on the phase is equal to 0, and this leads to a conventional continuity equation. So essentially, in the three-dimensional world, I will have a fluid. I'll pick a droplet. Okay, I pick a droplet. The fluid moves. So inside the fluid, I picked a droplet. This is my element of the fluid. Let's call it dV. That's my fluid. And the purple thing is a droplet that I visualized inside the fluid. So what is dV times rho at the point r at times t? It's a number of particles. This is a number of particles inside this droplet. Okay, now imagine that fluid flows and this droplet evolves. So what will happen? The fluid moves and the droplet changes its shape. Yeah? Imagine that you have a droplet, it moves and it changes its shape. As the fluid flows from here to here. But just by construction, the number of particles inside this droplet does not change. That corresponds to the particle conservation in the fluid. So given there is a particle conservation in the fluid, I know that the number of particles in the droplet does not change. So it means that if I follow the droplet as it moves through the fluid, its full time derivative does not change. Then Then I ask, what is the full-time derivative from the droplet in the fluid? And I know that the full-time derivative inside the fluid, it's a partial derivative with respect to time plus dr with respect to t times gradient of r. But what is dr over dt? It's the velocity of the fluid. And therefore, the full derivative with respect to time is the velocity of the fluid times gradient over r. And therefore, I end up having, from the condition d over dt rho is equal to 0, it implies that my fluid has the following conservation equation, and the quantity in the bracket is called current. So the situation I'm describing, so this was a quick reminder of hydrodynamics. So the situation I'm describing now is very similar. The only thing is that the fluid is not in an ordinary space, but it's in the phase space. So it has a coordinate which is r, and it also has a coordinate which is m, which is p, which is a momentum. So if I go back and write my equation, I have a function f of p, r, and t, and then the conservation of particles in the phase space, the droplet that
Can you
evolves.
go just a little bit up?
What?
Can you go just a little bit up? I didn't get to see the final. Oh, okay, thank you.
Then the conservation of particles in the phase space implies d over dt of f plus p dot grad p plus r dot grad r acting on f. And this is 0. So we ended up in having d over dt f prt plus p dot grad p f, also of pr and t, plus r dot gradient r is equal to 0. This thing is called a Alluvial operator or evolution operator. And like I said a minute ago, we're in the situation where we think semi-classically, so dr over dt, it's a velocity of a particle, and dp over dt, I'm thinking about this as a classical particles now, it's just a force that acts on a particle. Therefore, I can rewrite this equation df over dt plus EE plus E over CVP cross B grad P plus VP grad R on F is equal to 0. And this is the Boltzmann equation in the absence of collisions. or if you want, in the absence of any type of interaction between electrons and any other possible degrees of freedom. So if you start with, say, a given distribution, any given distribution, and apply external forces that are electric and magnetic field, then the distribution with the phase space will evolve in accordance with the equation I just wrote. Now, let us now discuss briefly what is it good for? How does it help us? What can we compute if we know the distribution function f of P, R, and T? What can we compute? So assume that we have solved this equation, we know the distribution in the phase space. What can be computed from there? Okay. So if I take the distribution function in the phase space and sum it with respect to momentum, what do I get?
So you get density of particles as a function of iron.
Correct. I get a density of particles of electrons. If I multiply it by energy, say non-interacting particles, I multiply by energy. And sum of all possible momentum, what do I get?
You get the total energy?
I get an energy density. I get energy density.
Yes.
Energy density. So the first thing would be then particle should be particle density. If I multiply by energy of a particle, I get particle energy density. If I multiply it by momentum and sum with respect to momentum, what do I get?
A momentum density?
A momentum density, correct. This will be momentum density. So once again, these are exactly if you want to go to hydrodynamics, these are exactly how the three fundamentally conserved quantities of classical hydrodynamics are defined. Particle, energy, and momentum density. These are the quantities that are defined precisely in this way. What happens if I multiply it by velocity? And sum with respect to momentum, what do I get?
Well, I guess it's just like before the velocity density.
Okay, so for parabolic spectrum, for epsilon p is equal to p square over 2m, velocity is just p over m. And for parabolic spectrum, I will get 1 over m momentum density for parabolic spectrum. And that's absolutely correct. However, for a general spectrum, for a generic spectrum, that's not necessarily true. However, what is always correct? What is this object? Think again, what happens if I multiply, what is written here? It's a velocity of the particle in the phase space times how many particles are in the phase space in this momentum, and a sum of all momentum. So what is this?
So it's like current.
It's a current. It's a current density. It's not like current, Polina. It is a current. And now what we see from these two equations, from this equation and the equation below, that for parabolic spectrum, for epsilon p being equal to p square over 2m, current density is equal to 1 over m momentum density. So these two objects are identical up to multiplication by 1 over mass. So for parabolic spectrum, current, particle current is 1 over n momentum density. Not necessarily correct for a generic spectrum. So we have a particle current, and we have what happens if I multiply f of p, r, and t with epsilon p and vp and sum over p. What is this object? So object before this was a particle current.
So it's an energy current?
That will be an energy current. So you see an intimate relation between physical kinetics and hydrodynamics that emerges from here. Now let me look back at Boltzmann equation once again for the collisionless version of Boltzmann equation. So let me look again. So what was that? df over dt plus v grad f plus force v cross b. This is the force gradient. This is the gradient in R space. This is the gradient in K space. F is equal to 0. And now let me take this equation and integrate it to some.
You used here C equals 1?
Yeah, okay, so C is here. Okay, let me sum with this equation with respect to P. So now look what's happening here. The first term transforms into sum over with respect to P df over dt. So this is d over dt, sum with respect to p, f of p, r and t. But we discussed this object before. This is a density of electrons in three-dimensional space. So this becomes d with respect to t of density at the point r at the moment t. That's the first term. The second term, sum with respect to p, v grad r of p. It's gradient of r. Imagine that velocity is just velocity of p, and this is exchangeable with derivative. This object, we said, is a particle current. Therefore, I'm getting a divergent of a particle current. And finally, gradient of P times force EE plus VC cross B, gradient of P. Acting on F. So if I write it as an integral over D3P, okay, let me ignore magnetic field for a second, then we'll be correct if you want. This is the gradient. This is a gradient of P, F of P. That this thing will be proportional to the F at the boundary, and this will be 0. So if you want slightly more careful, I can write it as a d energy density of states d over d epsilon f, and this will be density of states distribution function at energy. And well, no,
at the boundary, the distribution is 0.
Yeah, just a sec. I wanna formulate it nicely without cheating. So how do I do it? It's a gradient. It's a volume integrate of the gradient. It's a volume integrate of the gradient, and yeah, it's essentially proportional to the, so it's some, I can think about some, I don't know, shell in the momentum space, and then, and okay, there's some theorem that, so do you remember what is the, if you integrate the gradient of a function within a closed volume?
You mean Gauss?
Yeah, yeah.
So it's a surface integral over something.
It's a surface integral, precisely. It's a surface integral. So this will be a surface integral of the function f of p and r, yeah? And now this surface is as big as you want. And now because
and then you say at the boundary it goes to 0,
and it goes to 0 because f of p goes to 0 when p is large. This thing goes to 0, and therefore because at the boundary it's 0, and you can take a boundary to be at large energies, and there this function is exponentially small. This term goes to 0. Yeah, so that's the proof of it. Okay, therefore this term is gone, and therefore if you look at this equation, that what happened, that it became d rho over dt plus divergence of a particle current is equal to 0. And this is just a standard continuity equation in the standard hydrodynamics. Very basic equation. So what did we learn? We learned that there is this object called distribution function in the phase space that is an extension of normal density that we used to in hydrodynamics. We see that from this, if we know this distribution function, we can easily find densities of our ordinary observables. We can find a particle density, we can find a momentum density, we can find an energy density. We can also find currents, particle currents, momentum current, energy current. So if we are able to compute the distribution function f, then we can compute everything we like. Yeah? All the familiar objects from transport theory contained in the function f. So if we know particle current, we know conductivity, electric conductivity, we know energy current, we know thermal conductivity, and so on. So all set of standard transport coefficients can be computed within kinetic theory. Of course, under certain conditions, of course, it will not be exact. Of course, we need to specify the range of applicability. However, the general idea, I think, is pretty clear. If we allow to think semi-classically, we can compute a distribution function f, and from there extract all what is called standard kinetic coefficient, all kind of response coefficient we would normally measure in condensed matter. Now, so far we consider a very simplified version of Boltzmann equation. We consider the equation where particles did not interact. The only source of interaction was an interaction with an external field. So essentially what this equation showed, that there was an evolution of, there was a collection of particles, each of them evolved independently of others and moved in accordance with its own second law of mechanics, with its own Newton law. So we had a collection of particles, particle had a momentum and coordinate, and this particle moved in space independent of other particles. And so this was a collisionless propagation of particles in the phase space. Very simple picture. Each particle moves according to classical equations of motion and independent of other particles. This is a very simple picture. It's a particles in the vacuum, if you want. Now, we need to complicate this picture. We need to say that real materials are more more complex, and real materials have interactions. And there will be 3 types of interaction we will consider in this course. So there's an interaction between the electrons normally Coulomb interaction. That's the interaction number 1. Sometimes it's called electron-electron interaction. There is interaction between electrons and the lattice. So this is electron-phonon interaction. When electrons and phonons interact. And the 3rd type of interaction, it's an interaction between electrons and the static disorder. Interaction with imperfections of the lattice. So these are 3 fundamental types of interaction that should be added to the Boltzmann equation that we have not discussed today. Okay, and what we will do next, and this we will do next week, we will start to account for these interactions, and we will start to extend this treatment, going from non-interacting electrons to electrons that interact with all these degrees of freedom, and see how it determines the transfer property of the system, and what we can learn about transport in the system once all these types of interactions are accounted for. Okay.
Can you please explain again the last note?
What?
About next week?
So we will start discussing the interaction between electrons and the static disorder. We will learn how to incorporate into the Boltzmann equation that we wrote so far without any collisions, the processes of interaction between electrons and disorder.
Okay.
So this is the story. This is a separate story of disordered metals that we will discuss next time. Do you have any questions about what we discussed today?
Can I ask some question about the general questions about the course?
Yes, please.
Do the lectures are usually take? Do they usually take this time, like about almost 2 hours, or more or less?
Well, more or less, yeah. I
usually
stop when the logic, when one chapter is finished, and I don't want to start things that I'm not.
We're expected to usually finish around 6 o'clock.
Yes, something like that, yeah.
Okay. And how is the grading of the course made?
You'll be given a number of home assignment, And the grade is based on this exercise.
So no test, just homework.
Yeah, just homeworks. You'll be given like 5 home assignments.
Okay, so the frequency is about 2 to 3 weeks?
Yeah, something like that, yeah.
Okay, thank you.
Any more questions? Well, if not, then see you next week.
Thank you.